It's extremely expensive, and what we're doing is we're developing a whole system of methods to quantify ribosomes, to quantify polysome loadings, which we can then use to model protein synthesis, to model translation rates, costs, and to provide insights into the reasons why the timing of growth is changing. This allows us to link back cellular growth to metabolic turnover. And the other thing that we're doing is developing tools to track ribosome biogenesis, so we can actually see when plants are growing by asking when are they making ribosomes. And I think with that, the acknowledgement slide. Well, first of all, I'd like to thank you all for bringing me to Argentina again. This is the group. I tried to put pictures on. A lot of the work was done by, actually I jumped over John Lunn, Ronan Sulpice, Eva Poole, and Joachim Fizan, and a very close collaborator, Alison Smith in Norwich, and Andrew Miller in Edinburgh, with whom we're carrying out a lot of our clock experiments in a very, very close interaction. It's really fantastic working with the top clock modeler. And this down here is a sort of a sketch of how we see the clock interacting with metabolic modeling. The clock is up here, and any resemblance between where the clock is and Homer Simpson's brain is an accident.
Thanks, Mark. Is there any question?
Mark, does the system somehow account for the days and nights being different in length in spring, summer, and autumn?
I think there's a double question. I thought there's a double question there, but yes. And the plants fit their metabolism exquisitely to the photoperiod. But specifically, if they notice the difference between photoperiods getting longer and shorter, my guess is how Arabidopsis might not do that. That becomes very valuable in things like trees and longer plants which are flowering, which Detlef might talk about. In fact, that's one of the slides I jumped over, and I can actually say, don't believe that what I said for Arabidopsis is true for all living organisms. We've done a meta-analysis on trees living in extreme stress conditions, high temperatures, no water, no photosynthesis possible, and those things can survive for several months quite happily and then grow again when the water comes back. So, plants vary.
Okay, there is time for the last question. Marcelo?
Is it working? Okay, so you mentioned something about unpredictable fluctuations in the environment. I was wondering how this system managed to, when you have a cloudy day or in the middle of the day and then the sun gets up, so is it, how does the rate of starch degradation being controlled? Is the level of starch at the beginning of the night that is the key?
The idea we have at the moment is the plant actually can't have that much control over the short-term effects on how much starch it makes. That's why the regulation of the degradation is so exquisitely regulated by the clock. If you have change of photoperiod, so the plant's growing in it, then in short photoperiods it makes much more starch. That's why it's not growing. It makes much more starch. Long term it can do it, but short term it can't, and therefore it's what happens in the night, which is the crucial regulation, I think, for keeping the balance in very fluctuating conditions. But we have a large set of experiments actually set up at the planning at the moment to see if we can discover any general rules about how the plant is coping with these fluctuations. We have one or two ideas. It's not total chaos, but we haven't done the experiments yet.
Okay, thank you very much. We can thank Mark again.